Okay, so I was going to go over working some of the problems and put on the YouTube channel. So I want everybody to know right now, don't panic over your grade on Chapter 1 Inverted Lecture. It's going to be okay. You're just learning how to answer these questions right now. So I'm going to go through and I'm going to work these problems and talk to you about them. I'm not going to write everything down on the inverted lecture itself. So don't judge what I'm writing in terms of words to be the same as what I expected on yours. I'm going to show you what you needed to draw and how you needed to work in that regard and how to answer the questions. So question 1 was actually 2 questions. The first was, what is the molecular formula of the following organic molecule? So you needed to answer that specific question first. And so what you needed to do is tell me how many carbons, hydrogens, nitrogens, and oxygens are in this particular molecule. And the easiest way that I have to go about doing this is to actually put a circle or a dot everywhere that we have a carbon atom. And so we have a carbon atom here, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we have 15 carbons, so that's C15. Now we need to figure out how many hydrogens we have. And so I use check marks or whatever I need to do to determine the number of hydrogens. And so what I notice in this particular carbon, it has 3 valences taken up, so it needs to have 1 hydrogen. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, and then the 1 hydrogen on the oxygen is 23. Notice this carbon right here did not have any hydrogens attached to it because this carbon has 4 bonds. Likewise, this carbon atom had 3 bonds to the nitrogen and 1 bond to the other carbon, so no hydrogens there. And of course, we have 2 oxygens and a nitrogen. So that is the molecular formula for this particular structure. Now, what kind of structure is this? This is either a bond line or a skeletal. I would have taken either answer there. So this is a skeletal structure. You should have had both of these answers correct to get full credit on that problem. The second question asks, explain why rotation can occur around a sigma bond but cannot occur freely around a pi bond. Okay, so you should have had a narrative describing a sigma bond and a pi bond, but what we needed to do was also use a figure. So a figure was needed for this particular question, okay, because it says up here in the general directions that you should use figures and schemes where appropriate. And so I'm not going to draw all the orbitals between 2 carbons because it's not relevant. But if you imagine a carbon atom that's sp3 hybridized, it will have an sp3 hybrid orbital and another carbon atom that has an sp3 hybridized orbital, and they will overlap in such a way that you have bonding around this axis. Okay, so now if you imagine having another bond here and here so that we can tell what's going on, if I rotate around this bond, okay, such that we have the 2 hydrogens now on the same side, if you will, what you'll recognize, if we draw in the orbital, that there is no change in that overlap. It doesn't look like the bond has changed at all, and that's because it's cylindrically symmetrical about that. And so that's what you needed to describe for a sigma bond. Okay, you needed to describe something like that in words and in figures for a sigma bond. And then you needed to do the same thing for a pi bond. And so if we think about a pi bond is, for example, 2 carbon atoms connected together by a sigma bond, which I'm just going to represent by a line, and then the 2 p orbitals on the 2 carbons that are overlapping one another above and below the plane. So that's what a double bond is when the 2 p orbitals come together. Now if I imagine rotating around this bond 90 degrees, just like I did here. Well, here I rotated 180 degrees, but here I'm going to rotate 90 degrees. Okay. if I imagine rotating 90 degrees, the two carbons, the sigma bond doesn't appear to have changed. But in fact, the p orbitals will now be 90 degrees to one another. So we have the p orbital that's in the plane of the paper, but now we've got a p orbital that's coming out of the plane of the paper and behind the plane of the paper. And so they no longer overlap each other, and we actually break the bond. We are breaking the pi bond in doing this. And so breaking bonds always takes energy. And so that's why you cannot freely rotate around a pi bond, but we can freely rotate around a sigma bond because we're not changing the overlap of the orbitals in the rotation of the sigma bond, but we are altering the overlap of the orbitals in the pi bond. Question number 3 said provide the ground state electronic configuration for carbon. That's the first thing you needed to do, and that is going to be 1s2, 2s2, 2p2. Okay? And it asks, is the ground state electronic configuration of carbon consistent with it having a valence of 4? Well, the answer to that question is no, and here's why. We don't pay any attention to the core electrons. We're only going to pay attention to the valence electrons because they're the ones that's responsible for bonding. And if we draw this out a little more, with a little more detail, we'll have the 2s orbital with 2 electrons in it. And then we have the 3 2p orbitals, 2px, 2py, 2pz, and we have an electron in 2px and 2py, or in 2py, and nothing in 2pz. So if we look at this, can this ground state electronic configuration account for the bonding of carbon? And the answer is no. It cannot account for it because I can't easily get 4 bonds. The only way that I could get 4 bonds with the ground state configuration of carbon would be if the incoming atom would interact with the 2s orbital, which has 2 electrons in it, meaning that whatever's going to bond with it had no electrons, which is unusual. I could easily form bonds between the 2px electrons and the 2py electrons. Say a hydrogen atom could come in and bond there and share its electron. But the 2pz is vacant. It would have to have a bonding partner that comes in with both electrons or a single electron pair to form the bond. And while that's possible, it's not likely for carbon. And so this doesn't really account for the fact that we have 4 bonds for carbon that we normally see. And in fact, if it did do what I just described, we'd actually have bonds that are 90 degrees to one another. So if this is X, Y, and Z, the PX, the PY, and the PZ orbitals all lie on the Cartesian coordinates, and they're 90 degrees with respect to one another. And we know that the bond angles in a sp3 hybridized carbon are 109.5 degrees, not 90 degrees. And so that accounts, this doesn't account for the bond angle that we see in a typical carbon atom. So, why is it that carbon can form 4 bonds? Well, it's because these electrons hybridize into 4 sp3 hybrids. Okay, and so we've got 4 of them, and we can have 4 electrons in those orbitals. The orbitals are lower in energy than the atomic orbitals, and we can form 4 bonds that actually go to the shape of the tetrahedron. Question number 4, draw all possible bond line structures for C4H10O. And so the easiest thing to do for that is to actually use your model kit. So let's build 4 carbons. Remember, we need 2 of the black pieces to build a carbon. So I'm going to snap those together. I don't have 10 white spheres, which is usually what we use for hydrogen. So we're just going to use our imagination for the hydrogens. And we'll use the 2 red pieces together to form an oxygen atom. And let's see what we can do. Well, we can put all 4 carbons together. If I can get those pieces on. And now I have an oxygen atom that I can bond somewhere. So I'm just going to bond it at the end to start with. This is a valid bond line structure. This is actually an alcohol. This is an OH. One of these has to be a hydrogen. So I would have 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. It would be C4H10O. So that's one possible structure for this particular molecular formula. I could also swap one of the hydrogens here and the oxygen, and I can have this alcohol. That is a valid structure as well. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens here as well. The other thing I can do, I can't move this here because that would be the same thing as where I had it here, and I can't move it there because that would be the same as the one that I started with. But what I can do is I could switch one of these hydrogens with one of these N carbons. And I could make this particular structure, C4H3, 6, 9, and of course one here, so still a 10. I have that alcohol. Now I can also take this structure and I could remove this, and now I could put it on the end and I can have something different, which would look like and that's a bad drawing, forgive me, but it would look something like that. That is also C4H10O. So I've taken care of all the alcohols that I could possibly make with this particular structure. But the other functional group that has a single oxygen atom in it is an ether. And so we can think about making ethers out of this particular molecule as well. So remember, an ether is an oxygen that's bound to 2 carbons. So we could have that particular molecule, and I can move this here. I can have that structure. Are there any others that I can do that would have C4H10O? I don't think I can move this anywhere else because I'd end up back with, oh wait, yes I can. I can move that one over here and have a different structure. So I would have that as another ether. So I think that is all the structures that I can possibly do for the molecular formula C4H10O. Very important that you use your model kits because this allows you to account for all your atoms and your bonds really easily. If you're trying to do this on paper, it's hard to sometimes see what you can move. But using your model kit, you can physically take things apart and put them back together again and see how you can get things connected together. So Tina pointed out to me that I misspelled skeletal. I most certainly did. So I apologize for that. I've made the correction now. We should be good to go. The other 2 problems this one is showing the curved arrows to go from one structure to the other. These are just showing how we're going to use the arrows for resonance structures. I'm going to move a pair of electrons from the oxygen atom to form the carbon-oxygen double bond. In doing so, I'm going to have to move this carbon-nitrogen double bond to here. I'm going to have to move this carbon-carbon double bond to here. And I'm going to have to move this electron pair and this pi bond up onto oxygen there. And so this is how these 2 resonance structures can be represented. And this is how the electrons have to move to go from structure A to structure B. Question number 6 says list the rules for writing resonance structures. This is available on the slides from chapter 1. So I'm not going to go over those. You can look those up. But I did ask you, using an example of your choice, explain how to determine the major contributor to the resonance hybrid. So let's just pick an example where we have something like this. Let's go with, we'll just put 2 hydrogens there. I'll just put another group there. Doesn't matter what it is. we can draw a resonance structure for this where these electrons are moving like this, forming a carbon-nitrogen double bond. These are both valid Lewis structures. They are resonance structures of one another. This is the major contributor, and this is the minor. And the reason that I know that this is the major contributor to the resonance structure is because there are no charges. Here, there are charges that are separated. And so that's how, in this particular example, I would have determined that this is the major contributor to the overall resonance hybrid. Now, depending on what example you used, you may have had a different rationale for why you chose the major contributor. A lot of people gave an example but struggled on the explanation for why their major contributor was the major contributor. So you needed to refer back to those rules for writing resonance structures to determine that. So I hope the YouTube video helps, and I will see you all in class later.